So what we're going to do today is we are going to just review for the exam. We'll actually probably finish early, partially intentional because I'm supposed to be at a meeting where we are making recommendations for those who are applying for medical school and dental school starting at noon. I'll probably be late, but I want to be there as close to on time as I can be.
Exactly on time. You said give me the end of the minute.
You're right. He was exactly at the very last possible second of on time. So what is going to be on the exam that's calculus based? It could be one of these actual 5 things. Transient circuits, both RC and RL transient circuits. Amperes law, the Biot-Savart law, Faraday's law of induction, and looking at the electromagnetic waves. So let's review each one of these in order. First, transient circuits. Transient circuits, you have 2 equations to relate the voltage and current through one, an inductor, and 2, a capacitor. So those are what I circled there. So if you have an RL circuit, you're going to be using these 2. If you have an RC circuit, you'll be using these 2. So you're using the voltage current relationships for the 2. You're going to either make a loop or look at a node to make your equation. So you'll, for instance, say you're looking at a circuit that has that has a switch that has been in this position for a long time, and then at time equals 0, it switches down to the second position. So this side here stays fixed, and it's going to move from there to there. So if you're analyzing that circuit, you have to, draw your circuit and then say what's happening. Now, with the capacitor, what cannot change the instant you flip the switch? That's correct. V cannot instantly change. For an inductor, what can I instantly change? I cannot instantly change. Now, those statements are very important for analyzing the circuit, but not for the calculus part. For analyzing a circuit, you want to find what the condition was before the switch was flipped and what it was right after. And so if it's a capacitor, you'll find the voltage you had across the capacitor just before you flip the switch and say right after it, it's going to be the same voltage. If you had an inductor, it's the current that can't change. So you'd find the current through the inductor just before you flip the switch. And then that would be your current right after you flip it. Okay, now looking at the calculus, this switch flips. And so I'm going to, based on the problem that I've just shown you, what I'm going to be doing is calculating, and it could say voltage or current for discharge. How do I know? Because the picture said, and my word said, that I'm going to have at time equals 0, my switch will flip from being connected to the power supply to just going through a resistor. And so since it's going through a resistor, it's going to have the energy stored in the electric field of the capacitor dissipated by the resistor. So what I'm going to do then is focus on the circuit after the switch has been flipped. And I need to make a relationship between those two. So first, I said we have to use Ohm's law. Voltage across the resistor is equal to I times R. And the equivalent relation for the capacitor, which is current, is equal to C d voltage capacitor dt. And then I need to make an equation. I can use either Kirchhoff's voltage law or Kirchhoff's current law. If I use Kirchhoff's voltage law, I'm going to, well, first, you got to be really careful about directions. If my current is going like that, then which direction is positive on the resistor? It's actually going to be the bottom one. It's positive on the side that the current enters and negative on the side it leaves because a resistor dissipated, took away energy. And then we use the same sign convention for the capacitor. Remember, the capacitor doesn't dissipate energy. It doesn't take away energy. It just stores it. But it's if with that sign convention, as the current's coming in, energy is going out of the current and into storing energy. And so that's why the sign convention works the same for both. So I can look at this and I can make two equations. Kirchhoff's voltage law would say that minus VR plus VC equals 0. Or I could use Kirchhoff's current law that would say I resistor equals I capacitor. I didn't even label them, but using the two equations drawn, that's VR over R is equal to C dVC dt. So I have either of those equations I can make. What should I do to try to solve this to find what the voltage and or current are going to do as a function of time? Do what? Okay, put the variables in. Can you be more specific on how I'm going to do this?
Divide by C. No.
Oh, okay. Did you mean separate variables? Okay, I misunderstood that. You may have even said those words, and I just misheard. I need to do something else first because this has three variables in the red equation: VR, VC, and DT. Well, and T. So with three variables, I'm going to have to do something. Now, I could take this lower equation and take the upper equation and say, well, VR, according to that equation, VR is equal to VC, right? If I take this, that would give me VR is equal to VC. And so I could just say, that will give me just one variable by substituting there. And so I would generally say VC and now I can do exactly what you said. I can take this and I can then say, well, separating variables is going to be dt over RC is equal to dVC over VC. Now I have a sign that's wrong here, and I'm trying to figure out how I could have a sign wrong. I have a sign wrong because I know that it's supposed to be a minus sign here. And it's pretty hard to get a sign wrong at this point. The current in the two has to be the same. I mean, after all, I drew the loop there, the same current. And well, when what?
It's minus, it's negative V voltage of resistor. Should be minus the voltage of the capacitor.
This equation here, going through the loop, says otherwise, right? Because with the definition of the current direction, we have going down. Oh, wait, no, I made a mistake. Is that what you're going to come up with point two? Okay. Okay, there's where my mistake was. They're both going down. Okay. So then VR is minus VC. That fixes my sign. Now I don't have a problem. I was silly. Okay, so now you integrate both sides independently. How do you integrate both sides independently? Because one's only a function of time, one's only a function of VC. So they have to independently be true. And I have minus T over RC is equal to natural log of V over V initial. So take the exponential of both sides. E to the minus T over RC is equal to V over V0. And you get V is equal to V0, E to the minus T over RC. Now, there was a slightly quicker way of doing that probably. That is, I could have just taken this relationship right here and plugged in that VR. Well, no, it's not quicker. I could have plugged in my equation VR is equal to IR, taken the derivative of both sides, and then had an equation in current, but that would have been just as long. So either way works, and you get an equation for voltage. Now that I've found an equation for voltage, how do I find the current? Let's just go back to that. Take the derivative. And so there I have an equation for the current as a function of time. And it's giving me a negative current that obviously has to do with direction. Because if it's discharging, the current should be coming out of the positive side. Right? I do an arrow like it is charging, so that's why it's giving me a negative sign. So that is how you would do a transient problem with a resistor and a capacitor. If it's a resistor and an inductor, you're going to do the same exact method, except your equation for the inductor is going to be VL is equal to L di L dt. So essentially the same work, except for you have a different relation, hence the calculus varies a little bit. So that's the first thing. Next one, the integral form of Ampere's law. So you have this here, the circulation. You are not going to have to do this integral. Okay, that's there just for your edification, not for poking out eyes. That's what you looked like Alex was getting. So you need to be able to calculate that circulation. That is the integral of B dot dl around an imaginary loop that is closed. That little circle means imaginary loop. And you set that equal to mu naught times the current enclosed. Pretty straightforward. How did we use this? We used this for an infinite straight wire. We used it for a solenoid. I think that's all we used it for, isn't it? I think it is. What did we use? We used those because they had nice, easy to do symmetries. What did we use if we didn't have a nice, easy to do symmetry? The Biot-Savart law. So the Biot-Savart law, that's the one that we did more calculation with. That is the dB. And notice the only difference between the two forms of this equation is that r hat is equal to r vector over r. And so just substituting the r hat in there gives you the lower equation. Sometimes you like it one way, sometimes you like another. This one here is obviously the more complicated looking equation because you have a cross product in it. But you do it in very much the same way that we did Gauss's law, or Coulomb's law, excuse me, for finding electric field. You're going to take dB and find the vector components of dB. So you have that cross product, you find the direction from the cross product, you find the magnitude by evaluating the cross product, right? The ds cross r is going to then have a sine theta, where theta is the angle between ds and r. So you find your magnitude and direction, break it into components, and then you integrate each component. So you remember we did a couple cases. We did the case of a circular loop, and of course turn that outside so it looks like this. And we found the magnetic field out here due to current on that circular loop. And to do that, it was kind of simplistic because the distance, the radius, was a constant magnitude in all cases, right? This was constant in all cases. And so all that was changing as you go around was the direction. We broke the magnetic field up into its components. So using the right-hand rule, if I have a little piece of wire up here, and I'm going this direction with it, then I have ds cross r is going to be, that was supposed to be coming out toward you. So coming out toward you, and then the r vector is pointing from the, oh boy, in this case I have to remember because it's really important. Pretty sure the r vector is pointing from the wire to here. I should have looked that up. Look that up yourself before the test so you know what direction the r vector is, because it will obviously reverse your answer if you have the r direction reversed. So I have ds cross r, and the magnetic field from that little piece is like this. So I break it up into its components. And then I recognize by the symmetry that the y components that go around the circle, those are going to add to 0. And the x components are the only ones I need to worry about. I integrate up the x components. For that circular integral, it's very easy because I just integrate dl from 0 to 2 pi capital R, 2 pi times the radius of the wire. And we were able to find what the total magnetic field was. So that one was a very simple geometry. The other geometry we did was a much more complicated geometry. It was a wire and I gave you a finite length wire, and we were finding the magnetic field out here due to current going through this wire. And so then we had to take a little piece, and our r vector is now going to vary. A is fixed and y is changing. And so then we had to again use the right-hand rule. And so ds would be that direction. So ds, let me turn and face this way. ds cross r would be in. So with the geometry I've given you here, the magnetic field will be into the screen. That's good. I did have my direction right for the r because we get that same answer when we use our standard right-hand rule for direction of magnetic field. And so no matter where you are in the wire, it's going to make a magnetic field that's pointing into the screen here. And then we have to find the magnitude. So now breaking into components isn't a problem. The direction is the same for everything. But the magnitude changes with your position. And so then we had to go through our little tricks of, take the derivative of tangent theta, that's 1 over, or d theta over cosine squared theta, and convert our integral into just units of theta for the variable we're integrating, and then do the integral. So that was a more complicated. So that's the second thing that you could have there for finding magnetic field, the Biot-Savart law. Third thing you could have is Faraday's law of induction. All things considered, this is probably the easiest possibility because Faraday's law of induction is just minus n d phi dt. So you find the flux integral b dot dA for whatever you have, and then you take the derivative with respect to time of that. And in most cases, that's going to be pretty straightforward. Defining the flux integral b dot dA is usually as simple as b times a times the cosine of the angle between them, and then you take the derivative and you're done. And then the final thing, electromagnetic waves. Here are the Maxwell's equations, and I put on the equation sheet exactly these forms of Maxwell's equations, except for I went ahead and without even checking, I put a mu sub 0 there because I'm pretty sure I just wrote the equation wrong here and didn't notice in time. Right, if you look at the units, it's got to be there. So those are the equations exactly as they are on the equation sheet. You have Gauss's law. This is the one we almost always use. What is the integral of rho dV? That's charge. So we use integral of rho dV is equal to charge enclosed. That's what we used on the previous slide. I wrote it, well, you have it both ways on the test. So that hopefully is not going to be confusing. The reason I have integral of rho over epsilon dV here is so you can see the transition from the integral form to the derivative form. The rho over epsilon 0 stays exactly the same. The integral of E dot dA becomes del dot E. So you just see that transition. And then Gauss's law for magnetism, the only place you would use it is in the derivation for the wave equation. Well, you are not going to have to derive the wave equation, right? Because basically the only way you're going to do that is to memorize 4 steps. And while memorizing 4 things isn't demanding, it's not what we're about in physics. We're not about memorizing. I remember back when I was in organic chemistry and my teacher said, now you have to memorize this, synthesis and this synthesis. And I'm like, I don't want to memorize this synthesis. That's why I went to physics. We don't. Faraday's law of induction. What's different about this than what I wrote in the previous page? Well, we had, instead of the integral of E dot dL, I just had the EMF out here. And instead of having the derivative of the flux here, we have the calculation of the flux. So it's the same thing. And Ampere's law, you can see, of course, what part of this equation did Ampere add?
Maxwell?
Or Maxwell. Yes, I meant Maxwell. Yeah. Big mistake. Ampere added all except for what Maxwell did. Heck, good answer. Maxwell added that epsilon 0 dE dt, showing that you have an effective current when you have the changing electric field. So you take those. Here's a set of steps to finding the wave equation. The importance of this is that it gives us the wave equation, which sadly I did not write down. Trying to think if I have that in the right position or not. I think it must be like this. Like this? Yeah. So what's important about this? Well, del squared is the second derivative with respect to space. This is the equation that any wave must obey. This is a wave in electric field. Now, you can't have just an electric field wave because the derivation for this required magnetic fields. Right? So since the derivation requires magnetic fields, you can't just get to the end and say, the electric field can support a wave. it had to be electric and magnetic together. So what you would actually be doing with this is testing a function to see if it's a solution to this equation. So I could conceivably give you, let us suppose that electric field has that equation and ask you, is that a solution to the wave equation? Now, of course, you could always answer and just say yes, and you'd get how much credit for that? Yeah, none. Wouldn't help you. What you would have to do is to actually do the work. So taking the second spatial derivative, that would be that's what the del squared means. And since E is only a function of X, these terms here are just 0. And so that's going to be second derivative of cosine omega t plus kx. Let's just go through and do it one at a time. And then using the chain rule, the derivative of the inside, which is k. Then taking the second derivative, so now I'm taking the derivative of what I had above in green here. Derivative of minus sign is going to be minus cosine. And then I'm going to have another k, so k squared. Or if you prefer, which I do, I dropped off the x hats here, so I just put minus k squared e because I dropped off the x hats because I was only doing it in the x direction. Okay, so that's doing the derivative of position, doing the derivative with respect to time, using the chain rule, the derivative of omega t plus kx with respect to t is omega. And then the second derivative whoops. Is minus omega squared e. And so what I have now is the equation that says minus k squared e equals mu naught epsilon 0 times minus omega squared e, which will be true if k squared over omega squared equals mu naught epsilon 0 equals 1 over the wave speed squared. So the wave speed is and once again, let's check to make sure I did everything right. Speed, omega over k. Yep. So does it work? Yes, it works because this equation is given, it's a true equation provided the speed is the right value. So you actually determine the speed by looking at that omega and k. So that's how you would be asked to use that, is to check to see if the wave function is a solution to the wave equation. So I would give you a wave function, you wouldn't calculate it. And then you just take the second derivative with respect to time. Remember, those are partials. By now, you should be comfortable with the partial derivative. It's the easiest derivative because anything that you're not taking the derivative of is just constant. Like, so if it's d dx, anything that's not x is just a constant. Partials are easy. That is all of the calculus stuff that could be on the test for you. So, questions? I'm going to go back up to the top where it has them all listed. Gila.
Why is the bit of the transient circuits?
The what?
The transient circuits.
You want to see the work or which part?
I get to the point where you do the integral, then you get v equals v out v, and then I get a little lost.
Oh, okay, so just defining the current from that. So I took this equation here and I plugged this V in for VC. And so I have I is equal to, and so the C on top that's canceled is the C there. The minus sign, minus 1 over RC, here, let me write this one out in longer form to make it more clear. So this is equal to C times, and then the derivative of V naught e to the So does that make it a little clearer?